Welcome to Electromagnetic Waves Review Lecture 10.1. Upon completion of this, you should be able to describe an electromagnetic wave, describe the electromagnetic spectrum and its parts and their characteristics, calculate the speed of light and vacuum from a permittivity constant and the permittivity of free space, calculate the speed of light from the magnitudes of the electric and magnetic fields, calculate the intensity of an electromagnetic wave, and calculate the wavelength and frequency. Okay, now in a previous lecture, we discovered Ampere's law as modified by Maxwell by adding this additional term. And what I want to point out here is a changing electric field creates a magnetic field. Maxwell realized that a changing electric field induces a changing magnetic field, which induces a changing electric field, etc. And we call this magic electromagnetic radiation, otherwise known as light. Okay, now, it's fine to do this between the plates of a parallel plate capacitor, but what else can we do with this? Well, we want to create an electromagnetic wave. So we need a changing electric or magnetic field. It turns out the easiest way to do this is to create the changing electric field. So you build a radio transmitter. And here's a radio transmitter right here. This whole thing right in here. Okay, so what we do is we have an LC circuit, really an LRC circuit, but we keep the resistance as low as possible, because resistance just basically wastes energy. Okay, so we try to keep that as low as possible. You connect an LRC circuit to an antenna, and the antenna is made of conductors. And we drive the circuit, which is called an oscillator, at its natural frequency, at resonance, with a power source. So what happens then is, of course, the driven LC oscillator will set up a changing electric field in the antenna. That will create electromagnetic waves that travel outward through space and time. This is a radio transmitter. Now, this transformer here is an impedance matching device. Remember I mentioned that to you in the previous chapter? It basically matches the impedance of this to the load here, which is, of course, the transmission line and the antenna. This changing electric field in here makes the electrons in the antenna dance back and forth. They accelerate. Every time they change direction, they're accelerating. And that acceleration creates a changing magnetic field, which induces a changing electric field, which induces a changing magnetic field, and creates the traveling electromagnetic wave. That'd be well and fine, be fun to do, but you might want to use this as a communication device. So what you do then is you use another LCR circuit over here, and if you tune that to the same natural frequency as this, in other words, set up it so it's at resonant that same frequency, connected to an antenna, this again, but over here, okay, it will respond to and detect the electromagnetic waves that this one produced. And that is a radio transmitter and a receiver. This is how your cell phones work. This is the cell tower. Here's the phone. So what have you got? You have a changing electric field that induces a changing magnetic field. A changing magnetic field induces a changing electric field. Together, these are perpendicular to each other, and they're also mutually perpendicular to the direction of travel. And this is called an electromagnetic wave. Electromagnetic waves are transverse. The electric and magnetic fields E and B are always perpendicular to the direction in which the wave is traveling. The electric field is always perpendicular to the magnetic field. The cross product, E cross B, always gives the direction in which the wave travels. The fields always vary sinusoidally, just like transverse waves. Moreover, the fields vary with the same frequency and are in phase in step with each other. So FYI, there's a right-hand rule for this. You guess this one was coming. For electromagnetic waves, your index finger is the electric field. Of course, if you remember in a wire, the index finger is the current, right? And the E was in the same direction as the flow of conventional positive charges. In other words, the flow of conventional current. So that's your index finger. Your middle finger is still the magnetic field as it always has been, and your thumb now is V. And of course, you'll have to flip your hand at 2 times the frequency to get this to work, so it really wears you out. So we say that E equals E max times the sine of kx minus omega t, and B equals B max times the sine of kx minus omega t. Now, E max and B max are EM and BM. Those are just the amplitudes of the waves. V, of course, is C, and that's the speed of light, and that is E over B. And that also equals 1 over the square root of mu naught epsilon 0. And that equals omega over k. Omega is the angular frequency in radians per second, and k is the angular wavelength in radians per meter. Now, by the way, since these things are in phase, this formula holds. It doesn't matter whether you use the amplitude or use the instantaneous value or use the RMS value, because they're always in phase with each other. It's okay to use this. The magnetic field varies sinusoidally, inducing, via Faraday's law of induction, a perpendicular electric field that also vary sinusoidally at the same frequency. Because the electric field is varying sinusoidally, it will induce via Maxwell's law induction a perpendicular magnetic field that also varies sinusoidally. The two fields continuously create each other via induction, and the resulting sinusoidal variations of the field travels a wave, and that's the electromagnetic wave. Electromagnetic waves are the only type of waves that can travel in a vacuum. Every other wave requires a medium. Sound waves require a medium. They can't hear you scream in space. They can see you scream in space, but they can't hear you scream in space. That's because sound waves require air or something, or water or something to travel in. Electromagnetic waves travel better in vacuum than they do in anything else, and they're the only waves that do travel in vacuum. So the next time you step outside and feel the sunlight on your face, and think about that. There is a vacuum of space. There's 93 million miles of vacuum between the sun and the earth. And yet that sunlight comes across that vacuum of space and lands on your face. That's absolutely cool. Okay, now the speed of light is constant regardless of the frame of reference. Everybody, no matter how fast they're moving, measures the speed of light at a constant speed. This is the special theory of relativity, which we will cover in chapter 26. Now the meter is now defined so the speed of light in vacuum is exact. So the speed of light is one of these physical constants that is actually very useful. If you want to know the speed of light out to 9 digits, here it is. That's how much we know it now. Light is the fastest thing in the universe, but it is extremely slow when compared to the immense size of the universe. It takes a finite amount of time for light to travel. We just don't notice that because relative to us, it travels pretty fast. But in reality, it's really slow. If you look at something 1 meter away from you, do you realize you're seeing it as it is in the past by 3.3 nanoseconds? So if you look at something that's 2 meters away from you, it is 6.6 nanoseconds in the past. And if you look at the sun, please don't look at the sun with your naked eyes. If you look at the sun, it takes 8.5 minutes to reach Earth, for that sunlight to reach Earth from the surface of the sun. And the most distant naked eye object that we can see, which is the Andromeda Galaxy, it's our sister galaxy in our local group. It takes 2.2 to 2.5 million years for the light to reach us from that. And equally, if there are aliens in the Andromeda Galaxy looking toward the Milky Way, it's going to take that light 2.2 to 2.5 million years to reach them from our galaxy. This brings us to the topic of the electromagnetic spectrum. Recall the range of wavelengths of light, the electromagnetic spectrum. Light can have any wavelength or frequency. There is no upper or lower limit. Now, we have given names to various parts of the electromagnetic spectrum, mainly for convenience. The wavelength lambda and the frequency f are inversely proportional to each other with c the constant speed. In other words, c equals f lambda. As frequency goes up, wavelength goes down and vice versa. This is the electromagnetic spectrum, and I'm just going to point out some of the important parts of it. Now, at this end, which is the low frequency end, frequency is extremely low. The wavelength is very long, because remember, they're inversely proportional to each other. Not shown on this is the energy per photon. The energy per photon at this end is very low. As you work your way up to the right here, the frequency goes up, the wavelength goes down, and the energy per photon rises. Now, at this end, of course, this is your 60 hertz AC wall outlet, the 120 volts that comes out of your wall outlet. That's a 60 hertz electromagnetic wave that's transmitted through the wires of your house. It also gets transmitted from the power company to your house. And most people don't think of that, but that is actually an electromagnetic wave. Then you get into the radio waves. Radio waves include your AM band, your FM band on your radio, things like that. And notice there's overlaps between this. That's because nobody completely agrees exactly where one ends and the other one begins. Okay, microwaves include your cell phone. They might include your satellite TV, your Wi-Fi, also your microwave oven that you cook food in. Okay, now notice again there's an overlap between microwaves and infrared. Infrared would be what you feel as heat. Okay, if you hold your hand up near a hot object, you can sometimes feel in your skin. Our skin has infrared sensors in it that protects us from touching a hot object. Snakes can see in infrared. That's how they detect their warm-blooded prey. Also, infrared or night vision cameras use this thermometers so that they can point at you and determine your temperature. It measures the wavelength of the infrared light and converts it to a temperature. Okay, at this point, we come to the visible light spectrum. Now, the visible light spectrum is the narrowest part of the electromagnetic spectrum. On this diagram, this has been expanded to make it visible, pun intended, you couldn't even see it. Okay, so the visible light spectrum, which is what we can see in our eyes, Runs from about 4 times 10 to the 14th hertz to about 7.5 times 10 to the 14th hertz. Roughly, again, nobody agrees perfectly exactly where these are. Roughly about 700 nanometers to about 400 nanometers in wavelength. Okay, above that, we get to ultraviolet. Now, at this point, you start having damage to your cells in some way, shape, or form. Ultraviolet causes sunburns, skin cancer. It can also damage your eyes, including causing cataracts and macular degeneration. You definitely protect eyes and skin from this. As you increase and get here further and further to the right here, remember the energy per photon goes up, and so does the potential for damage to your skin, eyes, bones, and your cells. Okay, above ultraviolet, you get to X-rays. X-rays can penetrate soft tissue. They don't penetrate bone very well. They're used to X-ray your teeth and look for cavities, which of course is decay in your teeth. Okay, now you get up above X-rays, then you get into the really dangerous stuff. Gamma rays can penetrate your bone, your skin, and everything. This is why you don't want to be in a nuclear blast. Gamma rays are what is the danger part of a nuclear blast. And of course, as I say, there's no upper limit. Now this brings us to Maxwell's rainbow, otherwise known as visible light. The center of the visible region is about 555 nanometers, which produces a sensation that we call yellow-green. Limits of this visible spectrum are not well defined because the eye's sensitivity curve approaches zero sensitivity asymptotically at both the long and short wavelengths. If we take the limits arbitrarily as the wavelength at which the eye's sensitivity is dropped to about 1% of its maximum values, these limits are about 430 to 690 nanometers. However, the eye can detect electromagnetic waves somewhat beyond these limits if they are intense enough, and everybody's eyesight is unique. We usually round this region to about 400 nanometers to 700 nanometers. Now, not only do humans see differently from each other, but different beings see differently. Cats and bees can see ultraviolet. Rattlesnakes can see infrared. Now, the sun's peak emission is about 500 nanometers, which is green. So our sun is really a green star. Our atmosphere absorbs and scatters the blue light, which makes the sun look yellow, because you subtract blue from green, what do you get? You get yellow. In space, the sun looks white because our eyes and brains blend the colors into white. Okay, now we're going to derive CV, the induced electric field, and we'll also derive CV, the induced magnetic field. Now, this is a snapshot of the field, of the electric field and the magnetic field of a traveling electromagnetic wave at a certain instant in time and space. Okay, so here's the XYZ axis. The wave is traveling parallel to the x-axis or along the x-axis. The electric field is vibrating parallel to the y-axis. And the magnetic field is vibrating parallel to the z-axis. Remember, they're all mutually orthogonal to each other, all mutually at right angles. This height here is h, and of course, this represents the field at that instant of time. And first, we're going to look at the electric field, and we're going to apply the integral of E dot ds equals minus d phi b dt. And we can rewrite that, remembering Newton's dot notation, as minus phi b dot. Okay, and we're going to take this integral counterclockwise around this yellow box. Now remember, with a dot product, only the parallel sides count. So only the part where E is parallel to S counts. And of course, this is S and this is E. So only the long sides will count. So we have E plus DE, that's this side, times H, that's the S contribution. This part's 0 here because it's perpendicular. And then we have this side, and we're going to go minus, okay, because we're going against E. We're going around this direction. So minus E times H. And of course, this part's 0. And if you reduce that, it ends up being HDE. So then we say that phi B equals B times H dx. That just comes from phi B is just B times A. And A is just this area here, which should be H dx. And then we can take the time derivative of that and say that phi B dot equals H dx B dot. So in other words, remember the dot product is the time, the derivative with respect to time. And then we can say that HDE equals minus H dx B dot. And remember, the dot product is a derivative with respect to time. Okay, so we're going to convert this to partial derivatives because this is a snapshot in time and place. dE dx equals minus B dot is going to be partial V with respect to X equals minus the partial B with respect to T. The minus sign means that B decreases as E increases. So E will then be E max times the sine of Kx minus omega t. That's just the wave that we had before, the formula for the wave. We're going to apply this to this. So we say the partial V with respect to x equals k times E max times the cosine of kx minus omega t. Now this EM or E max is the amplitude of the wave, or the electric field part of the wave. Okay, and then we can also use the B equals B max times the sine of kx minus omega t, and we can take the partial of this with respect to time. The partial B with respect to time equals minus omega B max times the cosine of kx minus omega t. Now we can plug this into this above equation and equate it, okay, and don't forget the negative sign, and we can get rid of some like terms, and we wind up with k times E max times the cosine of kx minus omega t equals omega B max times the cosine of kx minus omega t. The cosine terms will drop out because they cancel. We can reduce this, and we find out that C equals omega over k. That equals E max over B max. So C is defined in terms of the amplitude of the wave. Now, it turns out because the E and B are in phase with each other, this formula also holds for the instantaneous values of E and B, and also holds for the RMS values of E and B. Okay, now we're going to do the same thing. We're going to derive the speed of light via the magnetic field. Okay, so now we have the magnetic field. We're looking at this part of the magnetic field. As before, the whole wave is traveling along the positive x-axis. The E field is vibrating parallel to the y-axis. The B field is vibrating parallel to the z-axis. And we're going to take this integral of B dot ds in this direction. We're going to go counterclockwise around the yellow box. Again, only the long sides will count because B is parallel. And remember, dot products, only parallel counts. So in this case, we say minus B plus dB times H. That's this part. Plus BH equals minus HdB. Now, phi E is just E times the area, and the area is just H times dx. That is the area of the box. So then we can say that phi E equals E times H dx. And we can take the time derivative of this and say that phi E dot equals H dx E dot. Remember, the dot product is the time derivative with respect to time. So then we say minus H dB equals mu naught epsilon naught H dx times E dot. We then want to convert this from this to partial derivatives. So instead of the time minus dB dx equals mu naught epsilon naught E dot, we can say minus the partial B with respect to x equals mu naught epsilon naught times the partial V with respect to time. The minus sign just means that B increases as E decreases. Okay, so B equals B max times the sine of kx minus omega t. That's the formula we had before for the wave. We take the partial of that with respect to x. That will equal k times B max times the cosine of kx minus omega t. We take the equals E max times the sine of kx minus omega t. And we're going to take the partial V with respect to time. And when you do that, you wind up with minus omega times E max times the cosine of kx minus omega t. Now, this and E max and B max or EM and BM are just the amplitude of the wave. Then we're going to plug it into this equation and equate them. And the negative sign, there's a negative sign here that drops out, if I remember correctly. Yeah, it comes out here. Looked at it for a second. Where'd it go? Panicked. Okay, so then K times BM equals the cosine of kx minus omega t. That equals mu naught epsilon naught omega EM times the cosine of kx minus omega t. So then EM over BM, these are just the amplitudes of the waves, or E max over B max equals 1 over mu naught epsilon naught C. And if we can solve this, it winds up that C equals 1 over the square root of mu naught epsilon naught. So this defines C in terms of the fundamental constants for electricity and magnetism, mu naught and epsilon naught. And this is further proof this is an electromagnetic wave. Okay, so what do waves do? Their whole purpose in life is to transport energy efficiently from one place in the universe to another place. And now we're going to quantify that rate per unit area of energy transport. We're going to call that the pointing vector. Okay, we're going to give it the symbol S with an arrow on top to emphasize that it actually is a vector. So the rate per unit area, that is the power per unit area at which energy is transported via the electromagnetic wave, is given by the pointing vector. This pointing vector, of course, is in the direction of travel of the wave because that's where the energy is going. And S is defined as 1 over mu naught times E cross B. The units in this, of course, watts per square meter. Since the electric and magnetic fields are always perpendicular to each other and always in phase, the instantaneous magnitude of the rate of energy transport is S equals EB over mu naught, or E squared over C mu naught, or CB squared over mu naught. And all of these are equivalent. Okay, so then we want to find the average power of an electromagnetic wave. The time average rate per unit area at which the wave energy is transported is S. This is called, as by definition, is the intensity of the wave. So S is the intensity, and we give that symbol I. Don't get that confused with the current. I'm going to try to use small I for current, okay, and a large I for this. But again, we run out of symbols very quickly in this course, and this is why you can't memorize your way through the course. You have to actually know how to apply the formula and how to use it. You have to actually know the physics. So S equals I, where I is the intensity, and that equals the RMS E squared divided by C mu naught. Or we can rewrite this as C B RMS squared divided by mu naught. Of course, the units for this is, of course, watts per square meter. ERMS is just our old UMRs we had before. It's just the max divided by the square root of 2. Okay, or 0.707 times E max. And of course, E max is the amplitude. The RMS is that average we talked about when we got hit AC, because this is AC. It's the same thing. Of course, E max is the amplitude of the electric field. Also, we remember that C equals E over B, and also equals ERMS over BRMS. And you can use this formula for instantaneous values for E and B, for the RMS values, or for the max. Because they're both in phase with each other, it's okay to do that. Point source of electromagnetic waves emits the waves isotropically. That is with equal intensity in all directions. This is very much like gravitational situation. Gravity goes outward from an object isotropically in all directions. There's an inverse square law here. The intensity of waves at a distance r from a point source of power ps emitting light isotropically is I equals P over A, where A is that area. Okay, as this thing spreads outward, that area, it's like an expanding balloon. The area gets larger and larger. And the area of a sphere is 4 pi r squared. So I is PS divided by 4 pi r squared. If you double the distance from a light source, you have typically 1/4 of the power per unit area, or 1/4 of the intensity. And that works just like gravity does for the same reasons. Oh, we talked about this before. The electromagnetic wave carries its energy in its electric and its magnetic fields. And it happens to carry half the energy in the magnetic field and half the energy in the electric field. The magnetic energy density, little ub, equals B squared over 2 mu naught. The electric energy density is UE equals 1/2 epsilon naught E squared. Now, you can see here we have, this is a typical energy, from 1/2 times a constant times something variable squared. 1/2 times a constant times a variable squared. And now this is the energy density. That's joules per cubic meter. Each component has an energy that's equal to the other and carries exactly 1/2 of the total energy of the wave. So little u equals 1/2 epsilon naught E squared. Little ub equals 1/2 mu naught times B squared. E equals CB, and C equals 1 over the square root of mu naught epsilon naught. And we can substitute into this, and we wind up with U equals 1/2 epsilon naught times the quantity CB squared. That also equals 1/2 epsilon naught times 1 over U naught E naught times B squared. Or we can say that UE equals UB. This proves it. Now, have you ever wondered when you go into a dead zone, someplace like your cell phone, you carry your cell phone in someplace where there isn't a connection, okay, there isn't a signal. What happens to the signal? Well, it turns out your cell phone uses both magnetic and electric energy. Now, in reality, it's much easier to build an antenna that will pick up electrical energy than it is to build one that picks up magnetic energy. So usually the cell phone only takes advantage of the electric part of the wave. Have you ever walked into a building and suddenly lost your cell phone reception? Have you ever wondered why that is? Well, it turns out the answer to that question is right here, and specifically right here. Now, many buildings are built with rebar. Rebar is reinforcing their metal rods that run down the inside of a concrete wall to make it stronger. Also, typically the concrete walls also have the electrical wiring and the plumbing. Together, that rebar and the electrical wiring and the plumbing form a Faraday cage, and electric fields do not penetrate Faraday cages. So if your Wi-Fi and your cell phone depends upon electromagnetic radiation and the electric field disappears, you're not going to be able to generate the magnetic field, which will not generate the electric field, and your signal disappears. That's the reason why you have to have Wi-Fi repeaters in buildings sometimes, because the Wi-Fi repeater will redo that signal. Okay, so it brings the signal into the building inside the Faraday cage. Otherwise, you lose your signal. Now, typically, those buildings are also built extremely sturdy, so they're often used as storm shelters, and they make some good shelters against lightning bolts, too. So if your cell phone reception disappears in a building, and you're in a thunderstorm and you want to make sure you're safe, it might be a good idea to stay where you are. It's for the same reason that this disappears. It's the same reason why it's a good shelter against lightning. Okay, now when you look at the North Star, which is Polaris, you actually intercept light from the star that is a distance of 431 light years. It's emitting energy at a rate of 2,200 times that of our sun. This is a big star. It's actually one that's evolved and will eventually die. The power of the sun is 3.9 times 10 to the 26 watts. We're going to neglect any atmospheric absorption. We're going to find the RMS value of the electromagnetic fields when the starlight reaches you. Now, just as with any of these example problems, you should work on this at home, copy it down in your notes, and then see if you got it right, sort of as a self-assessment. Okay, the physics of this is an inverse square law, and we're talking about the intensity, light, and power transmitted in an electromagnetic wave. First thing you do, you write down your knowns and unknowns. You're going to have to convert some of the units, and this is definitely going to stand out. You're going to convert that unit. You're going to have to figure out what the actual power is, so you're going to multiply these two. At this point, you also write down this is what you're looking for. You have you look up and find the formulas. Intensity, which we just gave, the RMS squared over C mu naught. It also equals the power of the source divided by 4 pi r squared. And we have this relationship, E over B equals C. At this point, we can start plugging in numbers. And I equals the RMS E squared over C mu naught, or PS over 4 pi r squared. We can combine that. And we can say that ERMS is the square root of P, that's the power of the source, times the speed of light times mu naught, divided by 4 pi r squared. And BRMS is just ERMS over C, so it's going to be the square root of the quantity, the power of the source, mu naught, divided by 4 pi r squared times C. Now we have to convert this power of the star into watts. If you multiply the ratio between the star's power and the sun's by the power of the sun, you'll get that. Turns out it's 8.58 times 10 to the 29th watts. You also need to convert the light year to meters. There are 9.461 times 10 to the 15th meters per light year. You can see the light years are going to cancel out here. R is 4.08 times 10 to the 18th meters. At this point, we're pretty well ready to start plugging numbers in. And we're using this formula. Here's the power of the star converted to watts. Here's the speed of light. Here's our old friend, mu naught. And we have 4 pi and, of course, the radius squared. It turns out the electric field strength is 1.2 millivolts per meter. We can also find the magnetic field strength. There's two different ways. You can either divide this one by C, or you can go back to first principles. So the RMS is going to be the square root of PS mu naught over 4 pi r squared C. Here's our power of the source. Here's mu naught. Here's the 4 pi. Here's the R. And of course, you've got to remember to square that. Here's the speed of light. BRMS is 4.1 times 10 to the minus 12 Tesla. Okay, now light can exert pressure on stuff. We don't think of that because the pressure is relatively small. It can also cause an object that it shines on to change momentum because it exerts a force, believe it or not. So we're going to flash back to physics for a second. Whenever you're doing work, the work will be the change in energy. And that, of course, will be the force through the distance. And, of course, the good thing about this, it's always just the direction of the wave travel. So then the change in energy is going to be F delta T, that's momentum, and times the velocity. And remember, this is going to be C, the speed of light. And the change in momentum will be the change in energy divided by V. That's just turning this around. So we have delta U equals the momentum times the velocity. And the change in momentum, it's just delta U over C. That's just turning this around. Maxwell showed that an object that is free to move will gain linear momentum as it absorbs radiation. And in this case, the direction of momentum change of the object is in the direction of the incoming beam of radiation that the object absorbs. Part of this depends upon the elasticity of the collision. In a perfectly elastic collision, the light beam will hit it and come back, reflect perfectly. And this means that the change in momentum is double that of a complete loss of momentum. So in other words, it's the difference between a perfectly inelastic or squishy collision, or it just sticks together afterward, and one that's perfectly bouncy. If we assume all the energy is reflected by the object, momentum change is 2 delta U over C. This always winds up between two values. One is perfectly absorbed, and that's just delta U over C. The other is perfectly reflected, and that's twice what the absorbed was. Now we're going to back up a little bit to change in potential energy. We can write that as delta U equals F delta T times C, so momentum times velocity. The force exerted by the power of the radiated energy is just delta U over C delta T. So it exerts a force too, light exerts a force, and that's just P over C. So the intensity is a function of power as it's distributed over an area. So the intensity is power divided by area, or power equals I times area, where I is intensity and A is area. So that combining these two terms together, we can find the force for total absorption or total reflection, and anything in between is defined as, here's for absorbed, I over C. Here's for reflected. Note, just like the previous slide, is 2 times what it was before. Okay, so there's that 2. So reflected is twice as much. Now, if the energy is partially absorbed or partially reflected, it's going to be somewhere between these two extremes. Okay, now pressure is the distribution of force divided by area. So PR is F over A. Then the pressure for total absorption, total reflection, anywhere in between. Here's what it is. Absorbed is the intensity divided by the speed of light. If it's reflected, it's just twice what the absorbed value is, so 2I over C. Okay, now we have an electromagnetic wave that's traveling west. The magnetic field is oscillating vertically and has a frequency of 80 kilohertz, an RMS strength of 9.75 times 10 to the minus 9th Tesla. What is the frequency and RMS strength of the field? The physics of this is electromagnetic waves. Write down the knowns, 80 kilohertz. Convert that to SI right off the bat. The magnetic field is 9.75 times 10 to the minus 9th Tesla, and we want to know the frequency and the RMS strength. The frequency, that's a trick question. They gave you the frequency of the electromagnetic wave. That's both components. We also know that C equals E divided by B. So E equals C times B. Here is our C and here's our B. Units conversion, 2.93 volts per meter. Okay, now the checkpoints should also be done at home. And then when you view the lecture videos or come back to class, check them off. If you got a whole bunch of them right, you probably know this stuff. If you don't, you need to review. Okay, now before the days of cable, back when dinosaurs roamed the earth, and I was a child, televisions had 2 antennas on them. One was straight and the other circular. Which antenna could pick up, if either, could pick up the magnetic oscillations? Well, it turns out this is the circular one. Remember the conducting loop? And you dropped a magnet through it. Okay, and then when that happened, the conducting loop would develop a magnetic field of its own, had to generate a flux inside of it, and if it's a conductor, it will generate an EMF and a current. We can detect that, and it can actually be used to help a TV receive a weak signal. Okay, consider the region of space that you're occupying. Which of the following types of electromagnetic waves are present around you? Okay, the peak of the radiation that's emitted is set by the temperature. At typical room temperature, that's in the infrared portion of the band. However, everything in the room actually emits radiation of all the wavelengths, okay, including the peak. So this means the correct answer to this is all of the above. Which of the following properties do visible light and ultraviolet waves have the same value? Speed. All have a speed equal to c in vacuum. In 1667, Galileo attempted to measure the speed of light by having 2 people hold covered lanterns on hills that are about 1.5 kilometers apart. That's a little less than a mile. One person would measure time. Then one of the people with a lantern would uncover it. The other person would then uncover his lantern when he saw the light from the first lantern. It would go back. So repeated attempts failed. To see why, we're going to determine the approximate time it takes light to travel the 1.5 kilometer distance. You take the 1,500 meters, you have to convert it to meters, and you divide by 3 times 10 to the 8th meters per second. Turns out to be 5 microseconds. The average human reaction time is 0.2 seconds, which is much, much larger, so the data is lost in the reaction time. Now, a radio transmitter has a vertical antenna. Should a receiver's antenna be vertical or horizontal to obtain the best reception? Now remember what's going to go on here. The electrons are going to dance in the antenna, and they're going to want to dance with the same amplitude that they have outside the antenna, or at least a reasonable approximation thereof. You want the antenna oriented in the electric field direction. If you orient it the other way, this oscillation might be rather weak. And there it is. The amplitude of magnetic field component of electromagnetic wave 1 is B. If the amplitude for wave 2 is 2B, how does the intensity of wave 2 compare to that of wave 1? It's going to be 4 times as much. Why? This is squared in both of these. E and B are squared. And of course, BRMS is just the amplitude divided by the square root of 2, but they cancel out. If you double the amplitude, you quadruple the RMS value and quadruples the intensity. Okay, thank you very much.